So unit 4 is our next unit here that we're working on. And this deals with chemical reactions. For the most part, most of this unit is going to be a review. There is a couple things at the end that will end up being new for you, which is called a redox reaction. And those redox reactions, when we get into those, you're actually going to understand and learn why we have oxidation numbers that we use for our periodic table. Remember the charges that you have on the different things, like your oxygen is a -2. That's referred to as an oxidation number. Okay, so that oxidation number, you'll be able to kind of understand why we have oxidation numbers and why they call them that once we get through the end of that unit. Okay, there we go. So introduction 4.1 is what we're working on today. Anybody not have one of these note packets? I have an extra one for some reason. All right, so matter, material that occupies space, contains mass. It can be organized into a couple different ways. We can have mixtures, which are substances that have a variable composition, and they're combined. When they're combined, it's a physical change. So if we have salt and water, that's a mixture. Okay, we can have a tablespoon of salt, or we could have a cup of salt in a gallon of water. They're both going to be salt water. Okay, variable composition. Mixtures keep or retain the properties of their original substances. Okay, so we have a couple, and we can separate them through a physical change as well. Filtering, distillation, all of the things that we talked about last chapter were examples of this. Okay. Homogeneous mixture then is visibly indistinguishable parts. So you can't see the different individual parts of a homogeneous mixture. Homo means the same, so it's the same throughout. Okay. Homogeneous mixtures are also very tiny particles. And we don't see the different parts. So salt water, the air around you is a mixture, a homogeneous mixture. You can't go, oh, there's an oxygen, oh, there's some nitrogen, it's just looks all the same. Okay, at least you hope it does. If it doesn't, then we got smog or pollution of some sort in our air. All right, heterogeneous then is a mixture where we have distinguishable parts, or we have certain parts that are very large compared to others. So for example, we could have colloids. So colloids, we have I got to figure out where I'm drawing on this thing. Colloids, we have larger particles throughout, but they are suspended in like water molecules, but they're not so big. So this would be like a colloid. Remember, colloids and any heterogeneous mixture, when it's actually thoroughly mixed, is going to be positive for the Tyndall effect. So fog is a colloid. Can't see through it. Can't distinguish the parts necessarily, but there are bigger particles in there of those water droplets. And then you have suspensions where you have even larger parts that are in there. And then you've got a smaller thing like solute. So like if you had like mud in water, okay, it would be mixed up, but if you let the water settle over time, eventually those larger particles are going to sink to the bottom. Okay, those are heterogeneous mixtures. Any of these mixtures, because mixtures are physical changes, you can use physical changes to get back out of them. Filtering, distillation, chromatography, things that we talked about last chapter, I believe. Yes? All right. Pure substances then are going to be one constant composition throughout. There's no variation in that. So whereas here we could have a teaspoon of salt to a gallon of water, Or we could have a cup of salt to a gallon of water. This is not showing up great. That should be cup, not cub. That's all salt water. Down here with compounds, the composition is the same all the time. It's always 2 hydrogens to 1 oxygen. And that is your water. I don't know why this is not showing up here. 1 oxygen. It's like delayed. Okay. That's water. If we change that and we end up with 2 oxygens here, we don't have water anymore. Now we have hydrogen peroxide. Okay. So changing the composition of these, it doesn't, it's going to change the identity of that substance. You have to use chemical means to be able to split this stuff out. You can't use physical changes to make that happen. Elements also have fixed ratios, and that deals with their protons. So anytime we're dealing with 8 protons, it's always oxygen. We increase that by 1 proton, we don't have oxygen anymore, we have fluorine. So set compositions for these. All right, this is just kind of a flow chart that shows you kind of how you distinguish between these. So with matter, we have mixtures which have variable composition. If you can distinguish the parts, you're dealing with heterogeneous mixtures. They're also positive for the Tyndall effect when they're mixed. And then if we have a negative Tyndall effect, we have a homogeneous mixture. They're mixed thoroughly throughout. Over here, if we have a variable composition, we have pure substances. They're going to contain various types of atoms. If that is the case, then we're dealing with compounds. If it's not, then we're dealing with elements. Elements, then, the smallest part of those is an atom. And when we're dealing with the atoms, then, if they're in a compound form, we can use a chemical means to be able to separate it into the individual elements. Good? All right. So physical change, remember physical changes are without changing the composition. There's several types of physical reactions that can take place. Phase changes are always physical changes. Remember that. Phase change, physical change. Always phase. Come on, are you going to show up for me? There we go. So phase and physical. Remember that. The difference between these is that as we increase the temperature, what's going to happen with the intermolecular forces here? They're getting reduced, and then here they're gone, in an ideal gas at least. Okay, and then if we lower the temperature, we're going to start reestablishing those IMFs to eventually the point where we get to a solid. All right, as far as what these different things are called, if we are going from a liquid to a gas, that's called vaporization. There's 2 types of that. There's evaporation that happens at the surface, and then there's also boiling, which is a much more rapid situation. To go back from that, we have condensation. To go from a liquid to a solid, that is freezing. And then solid to a liquid is melting. They sometimes call that fusion. And the reason why you need to know that that's fusion is because we're eventually going to get to the point where we are taking this and we're going to go through fusion, enthalpy of fusion. An enthalpy of fusion is the energy that it takes to go from a solid to a liquid. There's no temperature change there, but it would be the energy that you would need to have happen in order to go from that solid to liquid. There's also enthalpy of vaporization, which is the energy that it takes to go from a liquid to a gas. Okay, we haven't gotten to that yet, but that's coming. I'm just giving you kind of a preview and why they're telling you about fusion here. You're like, what's fusion? Well, if you think about it, when we take and we go from the liquid to the solid, we're essentially fusing those atoms together in a solid form. We're reestablishing and really tightening those IMFs to give that a solid form. So that's where they get the term fusion from. Make sense? So if you're going from a liquid to a solid, it would be the energy that's released during that process out into the environment. Or if you're going from a solid to a liquid, it would be the energy that you would need to input in order to reduce those intermolecular forces. All right. Other types of physical changes, separations of mixtures, you can achieve those through like distillation. We talked about that. That was part of your last test. We talked about differences in boiling points. Filtration can separate substances based on particle size. And when you get filter paper, it actually comes with different types of filter paper that have different size filter paper. So when you get this, it normally has a number on it, and it'll tell you how much it would be able to actually filter based on that. So some filter paper is better than others. Just like you might have like a sieve at home, and then you've got another one that's like a real tight wire mesh. More things will go through the sieve with the holes in it than it would be the wire mesh that you would have. So just like you've got different things that you can filter out at home, the filter paper works in a similar fashion. We talked about chromatography, which we can use differences in polarity and intermolecular forces for that. Another type is deformation. That's when you cut, dent, tear, stretch, crumble, any of those sorts of things. And then making solutions is another type of physical change, because you're just taking those ions, you're separating them in the liquid, but then they're going to come back together if you dehydrate, like if it's salt water, you dehydrate the water. Okay. Well, there's a little debate on that one. All right, key feature of physical changes is that the atoms are not rearranged. The physical properties such as shape, color, texture, flexibility, those are going to be changed, but typically the physical changes can be easily reversed. Chemical changes, though, are much more difficult to reverse. So they're a much harder thing to get back. Production of a precipitate, you guys know what those are, where you mix two liquids together and you end up with a precipitate, a solid that's formed. You're going to need to be comfortable with working with those. We kind of previewed a little bit of that last chapter, and we're going to talk about a couple things. I give you 4 things that never form precipitates, and then we talk about things later on in this unit where they commonly do. So production of a precipitate, you've got a color change, light being produced, change in temperature oftentimes is that way. And if you think about like those, you've got sometimes in the first aid kits, you've got the cold packs where if you break a seal inside and the two things mix, you end up with that generating heat. A good example of light being produced where something like that is those glow sticks. If you've ever had the glow sticks before, where you kind of break them just a little bit in the inside, you can hear them crack just a little bit internally. They mix a couple things together, that's going to produce light. Sounds, and you can think about this in terms of like a fire too. Okay, if you start like a campfire, it's going to produce light. You're going to have heat given off, and you also have the crackling of the fire as well. You have a gas given off there too, so production of a gas. And then anytime you form a new substance where you've got new properties, that's evidence of a chemical change as well. All right, types of chemical changes then. Composition is what I refer to as synthesis, but sometimes you will see it like this. So you're taking two things and making it into one. When I taught this back in chemistry, I would talk to you about how this is like a marriage, right? Here is another example of that. Decomposition then is just the opposite. So you're taking one substance and breaking it down into two. I liken this to divorce. Here is single replacement. Somebody's dating somebody else. They dump that person and pick up a new person. Okay, and they're by themselves now. So single replacement. Double replacement is just kind of a messed up Jerry Springer kind of event, okay? So A is going to dump B, A is going to pick up D, C is going to dump B, but, you know, then they pick that. So C dumps D, but then they pick up. So you got two couples and they swap. Okay? And that's double replacement. Huh? Princess and the Pauper. Okay. Oh, okay. So it's a reversible reaction, huh? Okay. All right. So, and then we've got combustion of a hydrocarbon. Remember, with combustion of a hydrocarbon is a carbon, hydrogen, hydrocarbon material. It's going to burn in the presence of oxygen, okay? And when it burns in the presence of oxygen, that is combustion. That's going to give you your CO2 and your H2O as byproducts. We also have just regular combustion that's not a hydrocarbon. So that would be like Mg and O. That would also be a combustion reaction. It's in the presence of oxygen. Okay. All right. Double ionic replacement includes acid and base neutralization. We're going to talk about those coming up. We're also going to talk about precipitation reactions, and then we also talk about redox reactions. Redox reactions are oxidation reduction reactions, except for double replacement reactions. And like I said, we're going to get into those in more detail. All right, I do. And I'm going to try to do this on this tablet. We'll see how that goes, okay? So we're going to try to identify what type of matter is shown in this image, okay? So type of matter, first one here. What is this? Okay, it's a pure substance. Yep, I'll buy that. So I'll take a pure substance. Is it an element or a compound? Element. Yep, it's a pure substance and it's an element. They're both the same things. Okay. And is it a solid, liquid, or gas? Gas. They're not touching one another. Okay. Now, how did I know? Now, this is one of 7 things. What is one of 7 things here? What are the 7 things that this could possibly be? Brinkelhoffs. Yes, these are your Brinkelhoffs. So pick your favorite Brinkelhoff. There you go. There you go. Okay. That can be whatever one you want it to be. All right. Is this a pure substance or is it a mixture? Mixture. Is it a mixture of what? Okay, it's a gas. I'll buy that as a gas. What is this here? If we just had this isolated, yep, that's a compound. And this guy right here would be a diatomic element. It's an element. Yep. So one of your Brinkelhoffs again. Okay, whatever you want it to be. Yep. Okay. Mixture or pure substance? Mixture. Okay. And a mixture of what? What is this guy right here? So that's an element, right? And this would be a compound. Okay, so mixture of elements and compounds. Solid, liquid, or gas? Gas, good. How do we know it's gas? Because these particles are not touching one another. All right. Yes, ma'am. Well, we haven't replaced anything. We're just asking what this is. Okay. So if we did this, let me take this guy. I'm going to put a red dot on these so that they're different. I want to make them a different element than this guy right here. Okay. So I put him so that you can distinguish this guy from this guy. Okay. If we took this and we went through a reaction and we ended up with red guy and orange guy here, and then blue guy over here. And I don't think I can change my ink color at this point, so I apologize. If this is blue guy over here, and this is the red guy, that would be a single replacement reaction, okay? All right, what is this guy here? Compound. He's a pure substance. And solid, liquid, or gas? Gas. Good. They're not touching. All right, what is this guy? Solid. Yep. A solid element. Yep. All right, what about this guy? Mixture. He is a gas, and he's a mixture of what? Two elements, right? Good? Working on these okay? Feeling good about these? Element and compound. Yep. Sorry. I don't know if I can figure out where I'm at on the page here. That's the problem. I'm trying to make this work. I'm doing the best I can. Okay, good. Making sense? Okay. All right. So for each of the examples here, determine if it's a chemical or physical change and how you know that. So take a second, talk to your seat buddy if you have one, and see if you can come up with an answer to that. All right, when we see evaporation, evaporation is a phase change. All phase changes are physical changes, okay? It's just simply evaporating out, okay? Just like if you had a sample of water and the water evaporates out over time, it's still water. It's water vapor in the air. It's just not in that container anymore. Here we've got a teacher's pants, small hole appeared. Now I haven't lost clothes to acid before, but I have lost them to iodine, ironically enough. I spilled iodine on my clothes one time and it ate little small holes through them. It was very sad. I was very sad about that. But if that lands on your pants, it's going to react with the material, the cloth, and go through a chemical reaction. And so it's not going to be cloth. You're not going to get those pants back again. They're done. So unless you like holy jeans. It can also eat through that into your skin and start burning your skin as well, by the way. All right. When a solution of lead nitrate and sodium chloride are mixed, we're going to get a color white precipitate formed. Anytime you get a precipitation reaction, that's chemical. And then Halloween, we've got dry ice. It's going to sublime. So sublimation is where you go from a solid to a gas like that. Okay. And then you also have deposition or deposition. That's where you go from a gas to a solid. So if you woke up this morning and you had frost on your car windows, that was that process that had happened overnight. Okay. So this is going, sublimation is where it goes from a solid to a gas. That is a phase change. Phase changes are physical changes. All right. Then that takes us to net ionics tomorrow.